Now, bar magnet as an equivalent solenoid. So here, let's derive the equation for the magnetic field at any point on the axis of the solenoid, the point that is outside the solenoid, and then here we will represent that particular equation in terms of magnetic moment. And we will see this thing, that equation is exactly like the equation of the magnetic field of bar magnet on its axis. Or in other words, we can say from that particular equation, we can prepare the equation for the magnetic field at any point on the axis of the bar magnet, as well as at any point on the equator of the bar magnet. Now see, as shown in the figure, we have a solenoid having total length that is 2L. So from the center of the solenoid, either side, we can take the length that is LL. Radius of the solenoid is A. Now on the axis of the solenoid, consider a point P, which one is at a distance R from the center of the solenoid, and R is greater than L. Okay. Now at point P, we want to find the magnetic field. Okay. Now see here. We know in previous chapter, we derived the equation for the magnetic field at any point on the axis of the current carrying ring having n number of turns. That is mu 0 n I r square upon 2 into x square plus r square raised to 3 by 2. So here we can consider the concept like this. If we consider the solenoid is made by this type of so many thin rings from one end to other end. And for each ring, if we take the magnetic field at point P, and then after if we take the summation of all those, we will get the resultant magnetic field at point P. So for that, first consider one infinitesimal thin ring on the solenoid having length of the ring equal to dx, which one is situated at a distance x from the center of the solenoid. Clear to all of you up to this? Now, first of all, we have to take the magnetic field at point P due to this particular ring. Now see here. Suppose the number of turns per unit length of the solenoid, that is small n. Now number of turns per unit length in the solenoid, that is small n, then the total number of turns in this particular ring having length equal to dx is how much? So number of turns in the ring, that is capital N, that is n dx. Now with respect to this ring, point P, that will be at a distance r minus x. So here now we can write the equation of the magnetic field at point P due to this ring. As per this equation, dB equal to mu 0, total number of turns in that ring, that is n dx, current I, radius of the ring, that is equal to radius of the solenoid, that is a square, into 2, then the distance of the point from the center of the ring, that is r minus x, square of it, plus square of the radius of the ring. So that is a square and whole raised to 3 by 2. So from this particular equation, we prepared the equation for the magnetic field at point P due to this ring, which one is under consideration. Clear to all of you? If we consider the solenoid is made by this type of large number of thin rings, starting from one end to other one, and due to each one, if we calculate the magnetic field at point P, and then after if we take the summation, we will get the resultant one. So for that, now we can use integration. If this particular integration, this equation is integrated from one end of the solenoid to other end of the solenoid, then we will get the resultant magnetic field. So resultant magnetic field at point P, that is equal to integration dB, and the limits are minus L to plus L. From the center, center is taken as 0. One end that is at plus L, other end that is at minus L. Now mu 0 n I is square by 2, that is constant, so it is taken outside the integration. So integration minus L to plus L dx upon r minus x whole square plus a square raised to 3 by 2. Now here, consider r is very much greater than x, as well as r is very much greater than a. So in that particular case, in this bracket r minus x, you can neglect x. Then compared to r square plus a square, you can neglect a square also. So resultantly, this denominator that will be r square raised to 3 by 2 means you will get r cube that is constant one, so again taken outside the integration. So now mu 0 n I a square upon 2r cube integration minus L to plus L dx. So integration dx, that is x, limits minus L to plus L, this part that is as it is. Now substitute the limits. So x equal to plus L, then minus x equal to minus L. So B, that is mu 0 ni a square upon 2r cube into 2L. Now we want this equation in terms of magnetic moment. Now see, as per definition, we can write magnetic moment, that is NIA, means total number of turns, I that is current, and A that is area of the loop. Now here, total number of turns in the solenoid. So small n, that is the number of turns per unit length. Total length of the solenoid is 2L. So n into 2L will give you the total number of turns in the solenoid. Then current passed, that is I. Cross-sectional area, that is pi a square. Now we want to introduce this m in this equation. So see, n, 2L, I are there. So to take area pi a square, here multiply and divide this equation by pi. So B, mu 0, n into 2L. So this n and 2L are taken together in this bracket. Then current I. Then multiply a square by pi. So pi a square. So here divide by pi also. So 2 pi r cube. Now see, n into 2L into I into pi a square, that you can represent as magnetic moment of the solenoid. So B, that is mu 0 into m upon 2 pi r cube. Now multiply and divide by 2. So you will get magnetic field at point P, that is mu 0 upon 4 pi 2m upon r cube. So from this one easily you can write, if on the axis that is mu 0 upon 4 pi 2m upon r cube, then on the equator you can write the equation mu 0 upon 4 pi m upon r cube. Clear to all of you?